Well, thank you for the introduction, Ivan. Like I said, I'm Cole Spencer. Ivan is actually my boss, so feel free to message him with applause and praise for my presentation at the end of this. And yeah, I'm here to talk about bottom ash and its use in concrete. So just to get started, I'll go over a little bit of context for this discussion in case any of you all missed this morning's session or are new to the topic in general. I'll then talk about the materials that we received for this study and discuss the characterization of them. After that, we'll go into a little bit of performance testing results and then some conclusions and ideas for future work with these materials. So for a brief overview, a lot of this Tom just said in his discussion a moment ago. The current state of things is that worldwide consumption of concrete is increasing, and fly ash is one of the most popular supplementary cementitious materials used in concrete. The problem being that the supply of readily available fresh from the plant fly ash is decreasing due to closures of coal-fired power plants. So one of the next steps, along with many of the suggestions that Tom gave us in his presentation, is to look into new materials, previously untapped sources. And one of those sources that I want to talk about is bottom ash. Now, in case there's anyone new here, to get us all on the same page, what are bottom ash and fly ash? Well, here's a very simplified schematic of a coal burning power plant. You can see the furnace on the left-hand side. That's where pulverized coal is injected and ignited. The ignited mass, what's left after the carbon is burned off, can either fly up out with the flue gases, that's what's referred to as fly ash, or it can fall to the bottom of the boiler and collect, normally in larger agglomerates, and harden into what we call bottom ash. So if we're talking about using bottom ash in place of fly ash, well, there's an obvious difference that we need to overcome. And there's some questions that come along with it. So the first challenge is obviously that bottom ash is going to require processing. It's not a powder, right? It's the size of aggregates. Bottom ash also, there's questions about its reactivity, about whether it'll work in the cementitious system. And if so, people are curious about how it compares to fly ash. So with that being said, to answer some of these questions, we gathered fly ash and bottom ash from 9 different power plants across different parts of the United States. And when collecting them, one of the goals in sourcing these materials was finding a range of calcium contents. As those of us who work in fly ash understand, things you think about when trying to guess at the performance of a given fly ash in concrete is going to be its calcium content. And so we want to be able to capture a range of that to make sure we understood those behaviors. And then in all instances where it was possible, we made sure that the bottom ash and the fly ash were sampled from the plant at the same time to avoid sampling errors. So the first part of this presentation is going to be material characterization. So we're going to start off with the physical characterization of these materials. And with bottom ash, that has to start with processing. So as I described, this material is large and it needs to be pulverized into a powder. We did that with the raw material at our lab by using our ball mill, our laboratory scale ball mill. And we decided to mill all these materials to a ASTM C618 fineness of 10 plus or minus 1%. Doing this allows us to take a material that previously required a sieve stack gradation into one that's a fine enough powder to use particle size analysis on. And speaking of particle size analysis, let's take a look at the particle size distributions of the materials that we sampled. So looking at these bottom ash particle size distributions, something you'll notice as the graph populates is that these distributions are bimodal. There's 2 predominant shapes to them, and that it's fairly uniform. Both of the humps tend to be about even. And when we take a look at the cumulative particle size distributions, we again see very similar shapes overlapping. This makes sense. We chose how much we were going to pulverize them, and we chose a metric to stop at. So it makes sense that we'd see that similarity. Fly ash, on the other hand, we didn't do any additional post-processing on. So this is the fly ash as received straight from the plant. And you can see that, again, we have a bimodal distribution, but these bimodal distributions are a bit skewed towards the finer side. The first mode is a little bit larger than the second. Additionally, looking at the cumulative distribution curves, we see that there's a lot more variation in the particle size distributions, which again makes sense. We didn't do any additional post-processing with these materials. This is as they were received from the plant. So also we should discuss the morphology of these materials. Now, microscopically, the powder of fly ash consists of these microscopic spheres. Bottom ash, on the other hand, is a different story. Like we saw on the micro scale or on the macro scale, it's rocks. It looks like aggregates. And after you pulverize it, it's still angular to a large degree. But interestingly, some other phases show up when you take a close look. You can see towards the top left of this image, there is what seems to be some sort of hybrid particle that could be partially crystalline, but also is even has a fly ash sphere embedded in it. And in the center of this image, you also see that there appears to be a fly ash sphere. So we were curious. We want to make sure we didn't have any cross-contamination of our samples. So something interesting we did recently was take this bottom ash sample, a raw version of it, before we processed it, and sieved it over a number 100 sieve, and took a look at it under the microscope. And you can see the material that passes the 100 sieve actually contains a significant amount of fly ash. This is a fun little discovery because these days, when discussions of fly ash and bottom ash come up, there are beginning to be questions about commingling materials. Well, it looks like bottom ash to some degree is already commingled. Obviously not to the extent that's being discussed. I just thought that was an interesting finding. Next up in terms of characterization is chemical characterization. So we're going to look at the crystal information as discovered by X-ray diffraction. So this first set of data, which is far too much data to put up on the screen at once, don't worry, I'm going to boil it down a little bit, is shows the phases that are shared by both the bottom ash and the fly ash. The main takeaway from this part of the information is the amorphous content and the quartz content. Doug Hooten this morning discussed about how bottom ash typically has a lower amorphous content than fly ash, which our data also shows that conclusion. So in order to make up that gap, there have to be some sort of crystal phases to fill it in. So one of the predominant ones appears to be quartz. In almost all the samples, there's a significantly larger amount of quartz in the bottom ash than there is in the fly ash. If we're going to look at the phases that only appear in fly ash, these seem to be more trace minerals. They don't seem to appear in particularly large or notable quantity. However, the remaining phases left in bottom ash to fill up that difference in the amorphous content are relatively significant in content. And predominantly, these appear to be albite, diopside, and akermanite. These appear to be mostly calcium, magnesium, and silicon-based minerals. Next step in looking at the chemical characterization is the bulk oxide composition, which we obtained via XRF. Now again, this is way too much data to put up on a screen and expect anyone to make any sense of it. So I'm going to put a little cheat sheet here at the end and show what I feel are the more interesting conclusions to draw. The first is that bottom ash tends to have higher silica and iron content than alumina content. However, in 618, we tend to look at the sum of the oxides of the sum of those three. And when you do add those all together, we see that bottom ash typically has a higher sum of those major oxides than fly ash. The next interesting conclusion to draw from this data is that the bottom ash, not always, but tends to have a lower calcium content than the fly ash. And the last, in my opinion, interesting conclusion to draw from this information is that the sodium equivalent, so sodium plus 0.658 times the potassium, tends to be lower in the bottom ash than in the respective fly ash as well. So the next step in terms of characterization that we're going to look at today is the way that ASTM C618 would characterize these materials. So starting with the fly ash, as I described in the introduction, we made sure to collect a range of materials that essentially fill the spectrum of calcium content. We have one as low as 2% calcium and one as high as 30%. Interestingly, this ended up having a range of different finenesses as measured by 618. We sort of saw that earlier in the particle size distributions. Then the resulting strength activity indexes were also fairly interesting. We have a number that are in the mid 80s, but then when we look at the higher calcium content ashes, we get all the way up to over 100%, 122% for our highest. The water requirements are also within the range that's typical of fly ash. You get a little bit of benefit in terms of your water requirement by using fly ash. It's also important to note that all the samples that were obtained and tested, these were all production fly ashes. As in, these weren't off-spec materials or they weren't marginal materials. These were regular production, could easily have been sold to a ready mix producer fly ashes. Now, if we do the same examination of bottom ash, let's be clear, 618 at the moment does not govern bottom ash. But if we were to look at it with those same requirements, we would see a couple of interesting observations. First of which being that, again, we see the calcium content increasing with a little bit of a hiccup there with source 6. But as we saw in the bulk XRF compositions, the calcium content doesn't seem to be as high in the bottom ash as their partnered fly ash. Also, interestingly, we see in some cases the LOI is too high to pass 618's requirements. This could be due to a number of reasons, potentially some native carbon content, some unburnt coal, some gypsum was identified in one of the XRDs. So there are a couple of reasons why that LOI may be too high and would need some form of remediation. Fineness, as described previously, we controlled that to grind it down to 10% fineness plus or minus 1%. The strength activity indices, on the other hand, are lower than that of the fly ash by a considerable amount. And that being said, they seem to be a little more tightly clustered than that of the fly ash. We don't see as large of a range. Keep that in mind for later. So clearly, all these materials don't pass 618 because of the LOI problems. Also important to note and interesting to note, that comment I just made about the strength activity index being not just more tight, but lower in general, it seems that the calcium content of these ashes isn't impacting the strength activity index in the same way that you see with C ashes and the same way you saw with source 7, 8, and 9 fly ashes in the last slide. So what are some intermediate conclusions we can draw from our characterization information? Well, first is that after processing the bottom ash, you still tend to get a bimodal distribution, at least when processed in a ball mill. And that bottom ash tends to have angular particles, but also contains some glassy structures and on occasion fly ash. From our chemical characterization, we can see that the bottom ash is more crystalline than fly ash, and that the additional crystal structures are normally quartz, diopside, albite, and acrimonite, and that the bulk oxide composition of bottom ash tends to have more silica, more iron, but less alkalis. And then lastly, in terms of 618 conformance, the bottom ash mortar strength seems to be less dependent and less influenced by the calcium content as ordinary fly ash is. And also the water requirement of bottom ash mortars is higher, probably due to the angular nature of the particles. So on to discussions of material performance. The data I have here to present today is on 2 different tests. First being the alkali silica mitigation test, ASTM C618. The second test being the bound water test found in C1897, previously have been referred to as the R3 test method. So we tested each of these materials, all the fly ashes and the bottom ashes, at 3 different replacement levels, 20, 30, and 45%. I'm going to click the slide to move forward here, and it's going to populate this graph one line at a time, and it's going to do it in order of the source location. And if you recall that the sources are also an ascending order of calcium content. So keep that in mind as you see the graph get populated. You can see that with 1 or 2 exceptions, as we increase the calcium content of our fly ash, we seem to have a lower ability to mitigate alkali silica reaction. Now let's see if we see the same impact in the bottom ash. So again, there are 1 or 2 places where that trend didn't exactly line up, but in general, it appears that in both fly ash and bottom ash, higher calcium content impedes your ability to mitigate ASR. This is a well understood behavior in fly ash, particularly given what we know, what we've already said about Class C fly ashes, and how the calcium content is easily soluble, which helps your strength, but could provide additional alkalis to negatively impact ASR mitigation. It's interesting to see that same behavior, although to a lesser degree, in the bottom ash, given that the bottom ash didn't seem to benefit from its calcium content in terms of its strength activity index in the same way. So this is a lot of colors and a lot of lines and a lot of data points to try to look at and draw conclusions from. So I provided another little cheat sheet. And what we can see here is that in most cases, the ground bottom ash actually outperforms the ASR mitigation of its respective fly ash companion. Now, obviously from what you see, that this is mostly being done and helped out by in the cases where we have middling to high calcium content ashes. However, source 2 is a true class F ash. I think it had around 4% calcium, and we still see that ash outperforms the fly ash in terms of ASR mitigation, which is an interesting finding. However, when we are looking at bottom ash, and when we're looking at any new material we're looking at to solve this problem that we've been discussing a lot today, I think it's important to keep in mind the mindset that Tyler Lay discussed in his presentation earlier this morning, which is we shouldn't be looking at if it's as good as we want it to be, or is it as good or not as the other thing. We should be able to evaluate these things on their own merits. And so with that in mind, if we consider the limit that's placed on ASTM C618, we can use that as sort of a benchmark just to guide the performance of the bottom ash on its own. And what we can see is that at 30% replacement level, 7 out of the 9 samples analyzed pass the ASTM 1567 requirement, which is a pretty significant accomplishment, particularly when you consider the fly ashes. Only 4 of the 7 seem to pass at that level. So what can we take away from this? Well, we can see that bottom ash, when properly processed, does have the ability to mitigate ASR. And in some situations, it mitigates ASR better than fly ash. Additionally, something interesting to note is that the performance of the fly ash, at least in this study, is a little bit more broad. It's a little more spread out. The bottom ash looks like it has a little bit of a tighter distribution of its data. That all being said, something that I think is really important to take away from this information is that while we're talking about these circumstances where the bottom ash seems to be performing really well and even better than fly ash, we're still looking at data that's in the same ballpark. We're not looking at a graph that could be some other strange material. In fact, if I handed you this chart, it could, without a label, it could easily be mistaken for results from fly ash, which is particularly interesting given these days all the discussions that are being had about potentially commingling sources or blending different types of materials. The fact that we're working in the same ballpark and that we're working with the same order of magnitude, I think makes it helpful in terms of meeting those goals. So the next test method, or the last performance-based test method we looked at, was the 1897 bound water test. Now, when we look at this data, what we first see is that the bound water of the bottom ash samples is slightly less than those of the fly ash samples. However, it is significantly higher than the inert materials we tested, so we can feel pretty confident that the bound water test is telling us that bottom ash is reactive to some degree. However, we can also see that the bound water results for the bottom ash are pretty tightly clustered, whereas the fly ash is a little bit more spread out. So let's take a closer look at this data and try to get a better idea of what's going on. And you can see that for the fly ash, there seem to be 2 different bands of data, one that's in the high 5% and another that's in the high 7%. This illustrates one of the aspects of the bound water test, which is that it's not particularly good at separating different types of reactivity. It just measures overall reactivity. And so the things that can influence that are, for example, in this first sample of the fly ash that had a high bound water, it's an exceptionally fine particle size. I think the D50 was around 7. The 3 on the other hand are the high calcium C ashes that have a large quantity of reactive calcium. And so when we plot, for example, the D50 against the bound water and the calcium against the bound water, you can see that these bands of data sort of show up, where you can see these different types of materials get isolated because of their unique ways they can take advantage of the setup of the bound water test. So what's the point of talking about all this? Well, first point is that it's interesting that we have these fly ashes that have these unique properties that make them perform particularly well in the bound water test. But those properties aren't, or that performance isn't reflected necessarily in the bottom ash samples. This sort of reinforces the idea that these materials are similar, but they're different materials, and to some degree, they'll need different consideration. Additionally, the narrow range of results in the bottom ash, while still having variable calcium content, indicates that the performance or reactivity of bottom ash in many systems is likely going to be governed based off of its particle size distribution. So another main takeaway of all this is that essentially the bound water test is useful for determining whether a material is reactive, but it doesn't necessarily describe what exactly is causing that reaction. So that being said, what do these performance results tell us about bottom ash in general? Well, first, the process bottom ash is reactive, and it can successfully mitigate ASR. And it can mitigate it as well as fly ash, if not better, in some circumstances. Next is that the bound water test is indicating to us that the process bottom ash is reactive. Check, that's good. And that the calcium content of the bottom ash doesn't seem to be latently reacting in the same way that the calcium content of the fly ash is reacting. Like I said, we saw that difference with the more tight band of data for the bottom ash bound waters than those high calcium fly ashes. Also, while the bottom ash and fly ash are suitably different, the performance in these tests are, again, similar to the ASR tests, a similar enough range to not potentially cause concern over blending or commingling in the future. So, that all being said, some quick conclusions, and then we'll wrap this up. So first is that ground bottom ash is a suitable material for use as a reactive supplementary cementitious material. That opinion seems to have been shared by a couple of different people giving presentations today. I'm glad to know that we're all on the same page. Next is that the reactivity of ground bottom ash seems to largely be governed by its particle size distribution, and that the differences in the chemical and physical characteristics, along with differences in reactivity of performance of these two different types of material, demonstrate how bottom ash is a distinctly different material than fly ash. However, they are not so different as to make them incompatible. So for future work with these samples, the next step is certainly concrete testing. We want to investigate the impact on fresh properties of using bottom ash, ground bottom ash. And also, of course, we just need data on concrete performance using these materials. We also want to do some additional durability testing, particularly focusing on ASR. We're going to be setting a lot of 1293s with this stuff. And then also, the topic that was not really investigated in this discussion is the topic of grinding specifically in terms of grinding to different degrees of fineness. And trying to find an optimal point where we can balance power consumption and energy used in the grinding process and your performance in concrete. Last, I'd just like to finish with some acknowledgements. I wanted to thank all the people and staff over at Testing Research Facility. All this work wouldn't be possible without the help of people like Hunter Culberson, Anupam Joshi, and Justin Brown. So thank you very much for your help. And also I wanted to thank my advisor, Dr. Kim Curtis over at Georgia Tech, for her guidance in all of this. And thank you very much. And that's all I have for today.